Hello everyone. This is Dilleswara Rao from Aeronautical department. So we are discussing on few classes on automatic control of aircraft subject. So previously we have discussed on displacement autopilot. So autopilot system, and before that we have discussed the solution of longitudinal equations of motion of an aircraft with the earth and body axis system, and stability derivative significance and its usage, and how that frequency response has been recorded for small changes we are giving for giving as the input for that one. And coming to that displacement of autopilot, what is its usage, and how this autopilot system has been designed for an jet aircraft and passenger aircraft, and also its upgradation and usages on fighter aircraft also we have discussed in last class. And that video, if you see that the displacement of autopilot system, so if you consider, if you go back to that video, you will find the what are the requirement things for displacement autopilot things we can choose for that. So now we are actually there was a drawback with the displacement autopilot is that it will be like when that root locus of that root locus of that Laplace operator, and the rate gyro system also we have the rate gyro system have been included on that feedback system, and due to that rate gyro system, how that signal and frequency response is being initiated, and how that frequency response is being further implemented with this pitch orientation system also we have just given a glance on last video. So now we will discuss on this pitch orientation system. So see here, this same the block diagram of an autopilot system has been that controlling system we have already seen in that last class. If you see this, the blocks of this autopilot system is that integrating gyro system, and there it is it will be given one voltage function, that is E, and that will be amplified with the amplifier, and then further after that amplifier, that voltage signal will be it will be improved. That voltage signal will be given to that summer. So from that summer it will giving to that elevator servo. From that elevator servo, that aircraft dynamic integrated system will control that servo motor motion, and that servo motor motion will be given to the control surface input. Like control surface input is like how much distance that control surface need to be moved. So on that phase, how this rate gyro system also, like a rate gyro system means what, how much distance it has to move, and that distance feedback also, if it is giving to that summer, then there will be like a in between feedback signal, in between feedback signal we are giving back to that servo motor, so that the servo motor can control the motion of that control surface, so that the thing will be perfectly operated. So how this will be operated, so that we will see it in this pitch orientation system. So see that the pitch orientation control system has an input desired pitch rate. Like if you are giving with a elevator and a flap input, if this system is being given to that elevator and flap deflection, so desired pitch rate or desired movement rate if you want to get, so such input plus the desired to obtain the type 1 system. The type 1 system is what, previously if you see that video in the displacement auto system, what that the root locus have been near to that system or not. When you see that root locus system for a jet aircraft, that frequency response and that short period approximation values have been near to that locus or not, that you can see it in previous thing. So here you see the type 1 system, which calls as an integrated forward loop. So makes an advisable use for an integrating gyro as a command receiver. So this see like pitch orientation system necessary for rate gyro depends on the characteristics of system. So the system is used to control the altitude of aircraft, and altitude and Mach hold control system can be used. Like I mean, whenever the pitch is being controlled with the system, so that what we will get, that altitude also will be controlled with this system only. So uh, so see, the pilot input comes from so-called maneuvering stick. So that a small stick which when be moved with the positions, the potentiometer, and thus produces a voltage. So the such system is referred to like a fly-by-wire system. Like fly-by-wire system, also we have seen in last classes. So what is that one? That here the control system input is being giving in terms of that signal only, voltage signal only. So that voltage signal will be traveled through that wiring system. So the introduction of this component redundancy and digital flight control system capable of detecting the sensors and other component failures, like when we are giving that voltage is, voltage input to that one. So there will be everywhere there will be a sensor for operating. Whenever we are operating that system, the sensor will sense that how much position that has been moving. With that position, will it that totally moved, or maybe in between any pause are there, or any in between connection is there, like that also it will be sense, and that sensor information will be immediately giving to that pilot console. So that error detection will be easily made by that system. So this fly-by-wire control system is like a practical system. In this system, that software detects the file failure at any point, any component, and isolate the file component failed components also, and transfer that operation or control redundant operational component. Like when the signal been given to that control system, and the sensor will detect that if any error is there, then it will bypass that system also. Like if in this line that the voltage is not traveling, then immediately that system itself will select the alternative way to pass that signal to that control system, so that the error will be rectified instantly. So that means that means what, that instantaneously that operation is being done without any errors. Like self-detective errors also been errors have been corrected, so that the operation will be smoothly it will be going on. So however, the manual stick does not provide any feel to that pilot, so that the pilot does not have that exert force or move the handle. So alternative method is to use the force stick. So I said that one. So previously, if you see, I said like when a doorstep example is there. So when we are operating one door, and the door will have a stopper, so that if the door is freely moving, and there is no obstruction force, so that we will move that door up to that level. Then we don't know like where up to which distance the door should be travel. So for controlling the travel, we will have a door stopper. The door stopper will stop the door movement up to the exterior extent level, so that we will feel that motion. Like up to here only, the door will be open. After that, it won't be moved. So that type of things we call it as a feedback system. That is like it is giving a message to us. So that is we call it as a feedback system. Like that, here also, when the control stick is moving by a pilot, so he doesn't know, like he doesn't feel that with this small movement, whole aircraft is getting that motion, and whole aircraft is getting that feel, and that fly altitude also been changed, or flight operation also changed or not. That feel may not be got by may not be felt by pilot. So for that portion, what he is given, some force stick movement been installed in this one. That means what, he has to apply some force, then only he will feel that. That means whenever he is applying that force, so that the pilot can feel like yes, with this force only that whole aircraft movement he's feeling that one. So like if you see, if you are driving a car and if you want to turn that car, you need to, today the cars are coming with power steering. So with that power steering, with a single hand only you can operate that one. But what will happen? Previously, there is like a warm gear mechanism only. So that warm gear mechanism, I think you've seen that warm gear will be like a very tightly it will move. So whenever you want to turn that one, also you have to apply for long forces. More forces on the steering, so that you will feel that yes, for turning this one we need to apply this much of force. But in aircraft it is not like that, no. So he has to feel that force is applying on aircraft, and for the force is feeling by aircraft or not, he has to feel that one. So for that, the arrangements also will be like this. So that you see here that block diagram of that control stick operation has been given here. So you can see this thing, like this is like a control stick, and this has been one strain gauge is been connected to that one, and it's a fixed point. And the torque amplifier is given here, like when we are operating that movement, so that due to that movement, like what that force, force is applying in this direction, so force into this one will be like a torque operating on this point. So the torque amplifier also like a voltage amplifier only. So here that signal will be like whenever we are giving that signal, so the signal will be amplified, and that amplified signal will be giving to that integrated gyro system. So that gyro system will be give the its direct motion. From here it will go to that summing amplifier. That means whatever the things, that input things are coming to here, that input voltage signal will be some club here, so that clubbed motion, that voltage signal will be applied on that controller servo. So this controller servo may be like any type. So I said that servo maybe electromechanically it will operate, like motors, electrical motors will be used, or maybe hydraulic or pneumatic motors also, pneumatic things also will be used. So here you see, so there will be like a electronic system and a mechanical system also being used here. So whenever this mechanical system is being connected and electronic system also being connected, so what is happening here when the signal is coming to here? So here the hydraulic servo motor, the hydraulic servo motor is being connected to that control surface. Here the control surface is elevator. So that elevator need to move here. So for that, what we need to do, when he is giving that signal to this one, so that the hydraulic servo motor will be operate. Like hydraulic servo means what? That actuator only. So that actuator type arrangement only will be there here. So that actuator will be operated. So that actuator signal, actuator input will be given to this one, so that it will be displaced maybe like that, or maybe like this. So like that, the operation of this control surface will be there. Okay. After operation, what will be happen? So that feedback should be given back to this gyro system. So like again, so maximum operation is maximum movement is been achieved. So that maximum movement message again need to giving to that control signal. So that feedback is being given here. So that feedback is given with this dynamics integrator. So with that dynamic integrator, that error function or feedback function will be feedback signal will be given here, and even that rate gyro in between that rate gyro feedback also will be giving to that summing amplifier. So that means what it will happen? This voltage will be both the voltages will be given here. So that input signal will be input signal will be come here, and which signal is being strengthened, that signal only will be again giving to that operation. So this loop is been continuously it will happen. And I said there will be an bypass operation also. That bypass operation is being given with mechanically linkages. So that mechanical linkages is been given to the this wall. So here that wall will be like what? So that wall will be mechanically operated or electronically operated. So if mechanically operated, what it will do? So that the mechanical input will be given to here, so that the wall will be open, then the hydraulic servo motor will be operated. So like this, there will be a two-way operation is being given here like a block diagram. So this is like a the pitch orientation control system for an steering stick. So you can see that stick is being necked down. That stick will be flex slightly when force is applied. So that stick will be installed with that within a system. The force exerted by the pilot will be pilot on the stick is rested by the servo actuator, which is being locked by a fluid trapped when the actuator valve is in off position. So it's electronically operated thing is being given here, and the mechanically operated thing is being given here. So see here, the result is the resulting force is applied on the control surface. So the deflection of control stick at the neck down area, the strain gauges of this position of the sense this deflection. So producing a voltage which will be command the signal. So for that case, the question is that the voltage is being amplified and is being fed into that torquing current. So torquing current means what? How much signal we are applying, so that much signal will be, the initial signal will be very low strength. So that the strength will be amplified. So that summing amplifier also been using here. So that voltage will be command so the torque current and the torque generator of that integrating gyro. So from the integrating gyro to the signal generator, so this signal is being amplified and using the position to selector valve of that elevator servo, positioning the elevator. As the elevator is positioned, the stick follows the movement, and then aircraft requires the desired pitch rate. So to maintain that steady pitch rate, the pilot must continue that apply pressure on that stick on the control stick. So the system is adjusted to provide any stick force gradient, the G of acceleration desired. So that's providing the desired feel to the tyre port. Like a pilot, like whenever he is applying on the force, I said no, he needs to feel that force is applying on that or not. So that arrangement also been given here. So in the future discussion of this pitch orientation control system, it will be assumed that the command integrating gyro comes from force stick. So it is in operated like control stick steering only. So this autopilot configuration is provide all attitude of autopilot only. So however, one important application of this is this is like longitudinally this operation is unstable. So that means CMA, that's CMA the stability derivative CM alpha is positive. So although the aircraft are designed to be statically stable, that means that CM alpha will be always negative. It should be lies in always negative. So the certain flight condition can result in large changes in longitudinal stability. So that such changes occurs in some high performance aircraft as they are enter in the transonic region. So however, even more that longitudinal stability results in a high performance aircraft, high angle of attack. So that phenomena, like the controlling phenomena of that high performance aircraft, will be call it as a pitch up condition. Okay, so that aircraft is subject to pitch up condition. So that CM versus alpha, if you see that graph here, so that CM versus alpha graph you see, so there will be like a whenever the alpha is getting increasing, so it will be coming to that negative values. After from the negative values, it is getting positive near to that positive means, that means what? That alpha values are getting into that higher. So with that higher position of, higher values of alpha, so that CM values also going to positive values. That means the aircraft is coming to unstable condition. So that means what? That the stable condition will be up to this region only. This region only, that this region is a stable condition. Whenever this point is reached, then unstable region is been standing out. Like there will be a range for that applying alpha values also. So the pitch up is most likely to occur in aircraft that have horizontal stabilizer mounted on well above the wing of aircraft. So in common place, it is top of the vertical stabilizer. So you see most of the aircraft for getting that, for getting more stability by the tail part. So if you see the importance of tail part of an aircraft is what? That is for stability purpose only. So aircraft won't be, if aircraft is only with wing, it won't be stable in flying condition. So if it is a tail condition, tail part is there, then only it will be stably fly in the air. So for that, position of the tail part and position of that horizontal stabilizer also will gives you that, will gives you the important role. So while positioning that aircraft, that vertical position. So see, this is a vertical. This is vertical stabilizer, and if it is a horizontal stabilizer, is on the top of that aircraft. So on the top of that horizontal stabilizer, so that the aircraft will be mostly stable condition. So that means if you see that CM versus alpha curve, so that whenever we are applying a small changes in alpha, so that easily it can be coming from a stable condition to unstable condition. So what happens if it is in middle position or down position also? So there will be, there will be a stable condition we can achieve, but for high performance aircraft, it won't be like that. So that is why you see that high speed jets and private jets. So most of that, the tail part will be upper side of that aircraft only. For subsonic flight and passenger aircraft, it will be like a middle part, down part of the tail only. Generally, that horizontal stabilizer will be placed on that fuselage side. That downside of vertical stabilizer only. But for passenger jets, or maybe like a high performance, high speed jets, that horizontal stabilizer will be placed on the top of that vertical stabilizer. So this is sometimes that end plate effect of that vertical stabilizer, and thus increases the effectiveness of vertical stabilizer. So another factor that contributes to this unstable flight condition is that wing with a low aspect ratio. So what is aspect ratio? Aspect ratio is the ratio between length to that breadth. So length to that breadth ratio is called it as a aspect ratio. If that aspect ratio is very less, that means what? If length is less and breadth is high, so that the value will be almost, it will be low only. So for that, such a wing with a large downwash velocity, and that increases rapidly as an angle of attack of that wing will be increased. So I said, whenever that due to that only, this swept wing condition also, been introduced here. So when the flow is flowing over here, so if it is very steep, like if it is a totally I mean if it is like a totally like a delta wing, even though that won't be stable for a higher aircraft, large aircraft. So the wing will be at least like a trapezoidal form only. So then it will be somewhat stable. But with this stable trapezoidal condition at the wing tip, due to that downwash thing. So downwash means I said that wing tip vortices has been created. So due to that wingtip vortices, wingtip vortices will gives you additional lift on the elevator side. So due to that additional lift, there will be a rapid change in that angle of attack. So to avoid, to avoid that, the wing aspect ratio will be at least in a nominal way. So see here that block diagram of another the control system of pitch up condition. So see again that one integrator block is here, and again that summing amplifier, and that summing amplifier, after that amplified that integrated signal, and that aircraft dynamic integrator also been given here. So why we are saying this one? So here this function defines CM alpha, that stability derivative solution is there, no? That stability derivatives will be always in differential condition. So that differential condition, whenever we want to solve that differential equation, we are using this Laplace operator S. So with this Laplace operator input, so that integrator function will be, whenever we are giving some function to that one, so that will be converted into that frequency response. So that roots are in real condition. So it we may not be correctly design that system, but if the roots are in in terms of frequency response, so that we can easily show that the values of that system will be like that. So see here, so that that TF, that for an high angle of attack, so Laplace transform, Laplace transform function is being designed like this. So for this system, so if you are applying for a different values of TF, high angle of attack values, so that is called delta is elevator angle input. If that elevator angle input has been increasing, so how that values will be go on. So for that, these are the equation conditions for that integrator input. So as the high horizontal tile moves into that wing wake, so pitch up occurs in downwash velocity. So pitch up occurs, so that downwash velocity also will be high. So due to this one, that this will be like a occur with the straight wing, and as well as the swept wing also. For swept wing, that aircraft, the forward shift of that center of pressure of that wing at high angle of attack is also contributing factor. Like for a swept wing, what will happen? Whenever the pitch is being applied to that one, that aircraft, that aerodynamic center will be moving, no? Like we said, this one. So this is the aerodynamic center and the center of gravity. So the aerodynamic center will be moving to and fro. So whenever that lift condition, that lift is been that lift is been moving, so that due to that lift force acting point, so that aerodynamic center also will move. So due to the swept wing aerodynamic center motion, so that is also will gives you that unstable condition for setting up that control system. So the practical solution for this pitch up problem is that limiting the aircraft angle of attack below a critical below a critical value. So critical value is you see that one, that CM versus alpha. So CM versus alpha condition, what is that one? So it is been started like that, and it has been end up here. So due to this one, so you can see, so up to here it will be a stable condition, and after that it is unstable condition. So that means what, this is the critical value of this angle of attack. So the limiting value will be this much only. So that means what, that whenever we are giving that control input to that system, that control input will be stop before reaching its critical value. That means suppose that the critical value is 0. Suppose if it is 2 degrees, so 1.8 degrees will be the highest value. That means that 2 degrees is the critical value, and 1.8 degrees will be the most maximum value. It won't be greater than that one. That means when we are giving that input will be almost equal to this 1.8 degrees only. Rather than that, it won't be give. So that means what? Before reaching the critical value only, that control system input is being controlled. So that type of arrangement we need to give for designing of control system to overcome this problem. So, thus the automatic control system of aircraft flyable angle of attack, that a critical angle increases the performance capability of that aircraft, so that the rest of things will be like the root locus study of this previous things. So like when we are designing that. I mean, that block diagram integrators and summers. So there, I mean, there we are getting that solution of that integrate the differential values only in terms of Laplace operator. So with that Laplace operator, for a different values, how that root locus values have been behaving. So that study we can do with that root locus things only. So the transfer function used to represent the aircraft representative modem, so high performer for a high performance aircraft. So although the transfer function of any aircraft can be designed with this root locus things. So see here, for a different aircraft, it's like root locus for an inner loop of control system, and root locus for an outer loop of root locus for an inner loop of aircraft system for different values have been given here. So this is the maximum value that response values have been following this type of behavior. And here you see it is been for a same that SRG and SRG values, that SRG values have been following this type of locus points. So that root locus study of both the stable and unstable condition demonstrate that factors influence the selecting of that rate gyro and integrating gyro system. So see here that figure 5. So figure 5 is the root locus for inner loop for a low angles of attack, and I mean low angles of attack, and that location of the closed loop poles are been situated like here. So the locations of the closed loop poles are for some rate gyro sensitives were used in figure 5 are shown. So these closed loop poles are open loop poles for outer loop. So that root locus for outer loop for the unstable condition is that will be seen in next figure. So that two values for rate gyro sensitive is been illustrated on that. So one value results the maximum damping region for that higher rate gyro sensitivity. So for that will be shown in that figure 6 you see. So here in the figure 6, if you see this one, so that root locus for inner loop for a higher angle of attack. So it has been that rate gyro sensitivity is been increased. So pole in the right half plane moves towards the zero in the left half plane. So that pole in the right half plane moves towards the zero in the left half plane. So see here that the pole is been given here. So the pole is been moving to zero on the left of plane, and towards zero on the left of plane, and the right of plane is moving towards to zero. So that means the additional pole at the origin, which results from that integrating gyro. Now the reason is for selecting high rate gyro sensitivity is being avoided. Like high rate sensitivity means what? So here you see the response between that locus point. So here it is been approaching to that zero, but it is going to like a asymptotic things. So whenever if you are approaching that value, for a high angles of attack, that rate gyro sensitivity will be highly implementive. Like highly implementive means what? It should be very sensitive to achieve that critical value. That means what? Whenever we are applying to that higher value, I said like that 2 degrees is the critical value and 1.8 degrees is the maximum value. So whenever we are applying that value, I mean that means we are supposed forcefully we are applying the control stick, and if it is suddenly going to that 1.8 degrees means what? That sensitivity is been very rapid. So I mean for small forces only, that sensitivity, that sensors are getting that feel and giving that value. But even though while they are getting that values of 1.8 degrees very rapidly, then what? That means that operation is being rapidly happening. So that type of things also we need to be avoid. Otherwise it will what it will happen, we can't feel that changes of that aircraft orientation. So that means that 1.8 degrees also slowly it has to achieve that one. Immediate action of that is not advisable. Okay, so that means if you trying to get this condition is like what? Whenever we are applying forces on the control stick, so that sensitivity, that rate gyro sensitivity means what? That rate gyro will sense that things are correctly applying on that amplifier, and that gyro system also getting that values very rapidly, so that feel is being given to that pilot. So that whenever it is achieving that critical value, before that only it will cut that signal. So like that, that rate gyro sensitivity sensor will be I mean the rate gyro sensor will be designed. So see here that another rate gyro I mean for that same thing only, for a high angle of attack and low angle of attack, how that root locus of pitch orientation root locus have been changed here. So see here, as you see, the rate gyro sensitivity is not not high enough. So that is the pole in the right half plane is too far to the right. The system is only stable for limited range or integrate limited range of integrating gyro sensitivities. So that the higher, you can see in the next table. So here you see that for a closed loop values of SRG for a different values, that 0.5 to 7.196. So for that, that root locus values have been changing like that. So here these values are approaching to that zeros very rapidly, but that approaching is been need to be that response will need to be very low. The root locus for the complete for high angle of attack is been designed like that. So for different values, how that integrating gyro sensitivity values have been designed means that two tables have been given here. So for point 0.23 and 0.527 values, what are the minimum value it is to achieve and the maximum value it is getting achieved? That values have been given here. So that integrating gyro system for instability for two rate gyro sensitivity. So that means suppose the two rate gyros have been installed there. So for that, what will be happen? So that for 0.23, additionally it is getting that 2.36 and 5.64. That means in between values it is getting for a low angle of attack. For a high angle of attacks, the maximum and minimum values have been designed here. So the integrating gyro systems will produce that stability that is shown in table 2. From this table, it can be seen that stability at high angle of attack can be obtained without producing instability at low angle of active attack. So to check the stability of that system, the control system of that aircraft is subject to pitch up at a high rate of angle, and that aircraft and the control system were simulated to analog the computer. So to add the realism, that mock-up of elevator servo with a four-stick input was tied into that computer. So that angle of attack will be displayed on an oscilloscope. So that several runs will be made during that which angle of attack was varied from trim angle of attack of that straight and level flight. So that response of the frequency response with respect to time is being recorded here for two things. So see, flight up to about 23 degrees of angle of attack, the recording of one of these runs, the neutral stability occurred at 13 degrees. See here, so for a time variance t seconds, so whenever the angle of attack is being increasing from 0 to that 23 degrees, so in between that 0 to 8 degrees and I mean that elevator angle theta and pitch angle alpha. So see here that the response is been here it is been stable and here it is been somewhat oscillated. So for a neutral lamp, that stability occurred at about 30 degrees angle, at which point that elevator angle is started decreasing. So that elevator angle, that theta dot is getting decreasing. So started decreasing, and as the angle of attack is increased still further, that elevator angle went through 0 and becomes positive. So that when you see here, so that that elevator angle is been delta is given here, no, when an alpha is been stable, so that it is getting that negative values, and after that it is getting to positive values only. And for here also that the theta values are getting to positive values only. So as the force stick was used to stick move forward, the elevator angle went to positive. However, it was still necessary to apply the back pressure of that stick. So simply the back pressure command pitch rate becomes 0, and the angle of attack return to its trim angle of attack. So beside that angle control, that aircraft that needs to pitch up, this control system would also be take care of trim changes, trim condition changes encountered in getting in aircraft passes through that transonic region, right? Whenever it is getting high angles of attack, so that the stable condition need to be achieved very rapidly. When it is getting that velocity values also higher, that means a transition zone, so that other zones also need to be calculated very rapidly. So this is all about this pitch orientation system. So here in the pitch orientation system, if you see that whenever that designing of the control system is mostly depending upon that angle of attack of that aircraft, and whenever it is getting transition from subsonic zone to transonic zone, how that high angle of attacks are been giving stability variations for that aircraft, and whether that variations are felt by that pilot or not, and what are the conditions for what are the condition required for feeling that force by a pilot also need to be designed by here by giving that two rate gyro sensitivity sensors have been installed on that block diagram, and that root locus behavior also we have shown here. Okay, so that's all about this pitch orientation system. So hope you can understand. So if you have any further clarification, we can refer these books for your further references. Okay, so that's all about this one. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.